Yes, class. Am I audible to all of you? Sidra, Fia, Deborah, Amna. Am I audible or not? Yes or no?
Yes, ma'am.
All right. So, yes, let us complete current electricity, at least in these two classes. Now, class, one thing I wanted to discuss with you. See, if we rush up with the syllabus right now, no, with current electricity, magnetics, these are not current electricity. Current electricity is will be done by tomorrow only. But chapter 4, that is magnetic effects of electric current, that is a very important lesson for your class 12th. All right, you will notice that all the concepts that you will be studying in chapter 4 will be coming. Chapter 5, 6, 7, 8, all these are very short lessons, those will be covered. But see, chapter 4, if we rush up for the syllabus purpose, then you will miss on the concepts and lots of questions will be missed on. So what I was planning, book 2, if we start simultaneously, right, on other timings, like before this class, or not today, not the next weekend, next to next weekend most probably, because second book is not linked, not ray optics and wave. I'm talking about ray optics and wave optics. Optics is not linked with your electromagnetism. Semiconductors can be linked. I mentioned semiconductors also in the class. So what we can do is that we can at least start completing the second book, right? So we do not have to rush up with the first book. So by the end of December or mid of December, we'll be able to complete the syllabus, right? That's what our target is. In the other batches also, which have been started earlier before you people, we have completed, we'll start with the second book. So with those, you can complete the second book, because ray optics, you will not use any concept of electromagnetism. So what will happen? Second book will be going, ray optics will be done, wave optics, it can also be done. And second book is comprised of that. By the time magnetics, chapter 5th, chapter 6th also will be over, because that's a very huge lesson. Ray optics is a very huge lesson. So magnetic effects of electric current, at least chapter 5, these will be over. So then your syllabus will also be stable, and then we'll be left with only small lessons. So end of November and mid of December, even before that, your syllabus will be completed. So I just didn't want to rush with this magnetics, at least chapter 4, because these first 4 lessons are very crucial for your physics basics. All right, so I'll discuss the timings right now. Let us focus on current electricity only, but just keep it in your mind. So it's just that you will have extra class. So extra classes this time will help you, rather than covering the extra classes at the last moment, because that time you people will be having your pre-boards also, right? And that time becomes very hectic. You people also can analyze, and in the I've the last batch which we had taken, so there also some students weren't coming in the month of December, because some schools had started with their pre-board, some had it in Jan. So before that, we should complete, no, before your pre-board start, at least we should complete with the syllabus, because you will be having revision classes here also. Here at Learnivio, we'll be having revision classes also. Yes. Temperature dependence of resistance and resistivity. This I wanted to discuss with you. See, on what factors does the temperature depend? Before this, all things we have completed, mobility and all the 4 points we have completed. So for conductors, just remember that when temperature increases, tau decreases. Tau means the average relaxation time, this decreases. So when tau decreases, the resistance or resistivity, this increases. All right. So when temperature and resistivity, this increases, you will get a straight graph, linear graph, which we call. So what happens is just a turn and twist over here, that initially before 0 degree is achieved, the graph is non-linear. It does not obey Ohm's law. Ohm's law we have studied, V is equal to IR, so it does not obey Ohm's law. So graph after crossing 273 Kelvin or 0 degrees Celsius, this becomes directly proportional. So straight away, straight linear graph that is obtained. All right. So this was the condition for conductors. Now, when we're talking about alloys, I hope you people know alnico and all, which are mixed, right? So alloys, same thing occurs. Same concept is there, but this concept is not there. Non-linear part is not there. Also, you can see the graph is so steep. You can notice the inclination is so much. If I calculate this angle, this would be around 45 degrees or something. When we are talking about these alloys, then the inclination is also not so much. Let me show you the graph also. See, same thing, both resistance and resistivity will increase with time and temperature. So here the inclination is not much. So when you are plotting the graph, be careful with this part, that the inclination difference should be there in your graphs. This question can come in your exam to plot the graphs. Moreover, this is a part of semiconductors. So again, I'm telling you, the way I mentioned in the beginning of the class, that semiconductors is linked with your first book. So semiconductors I'm not mentioning, but ray optics and wave optics, these are completely different. No concept of electromagnetism will be used. So if we start with the second book, no, parallel, simultaneously, which I was mentioning to you, we'll be able to complete the syllabus also on time, and we don't have to rush up with at least magnetics. Till chapter 4, your syllabus should go slowly. Then only you will see the concept. See, when we did electric charge in the first lesson, that charge had lots of effect which occurred till capacitance. Then when the charge started its motion, we have this lesson. Then because of motion of charge, magnetism will also be there. That we see. So everything is linked. That's why I'm saying these 4 chapters are very basic. So I don't prefer to rush up with here. Or one more point is there, that we can have extra classes and be completing this. But what I think is better, that if we start with the second book, because slowly we'll be going second book also in your extra classes. So your second book's major part, at least ray optics, that will be over. Rest of the lessons are very small. Wave optics is small, atoms, nuclei. Atoms is so small in one class, even not even properly one class is needed. Nuclei is very small because lots of portion have been deleted in your syllabus. Earlier, these were included. These were also proper lessons. Only semiconductors is so linked with these. Even some part of your modern physics, dual nature, atoms, nuclei, these are also linked. But optics is a complete lesson. So, and anyways, I'll discuss this in the next class only, because right now I'm not taking your extra class. Even the next week and also I won't take. After that, maybe. All right, so you will just have to attend extra classes. Let's see the timings and all. Okay, so yes, that was about alloy. Now, when we talk about semiconductors and insulators, these are inversely proportional. So this is a combination. It's like this combination you can remember. See, conductors, alloys, and semiconductors. I think I had it over here also. Here it is better. Here you can see. See, insulators, semiconductors, this graph, this is neat and clean. So here all the important details are on. So insulators and semiconductors, alloys, and this is for conductors, the temperature dependence or temperature variation. Now, see, last is superconductors. Superconductors are not very important from your examination perspective, but you should have an idea just in case in your MCQs, the first section A that you have, superconductors can be asked. So these are material that, see, they just know they have a particular temperature, which we call as the critical temperature. So once that critical temperature is achieved, there is a sharp inclination and variation in the graph. Those materials are called superconductors. So what exactly is the definition? A superconductor is a material that achieves superconductivity. Now superconductivity means what? Superconductivity means resistance is very less amount of resistance is present. That is what is meant by superconductors. So electric field interruptions are not present, magnetic field interruptions are not present. So a superconductor is a material that achieves superconductivity, which is a state of matter that has no electrical resistance and does not allow magnetic fields to penetrate. This is what is meant by superconductor. So what's the graph? Basically, for critical point, there is no variation. You increase the temperature, increase the temperature, increase the temperature, nothing will happen. As soon as this critical point over here is achieved, during the critical temperature only, there is an inclination in the graph. So gradually the resistance won't increase. See, if you look at the graph, try to interpret the graph. Here, temperature is increasing. Resistance is not increasing. Again, temperature has increased. Resistance is still the same. A very, very slight inclination in resistance when temperature is increasing. Slowly, slowly, slowly. And then it is increasing. So this is basically, we call it as exponential increase. This is increasing exponentially like this. Fine. This is what are all the graphs. So this can be a part of your current electricity and this can be a part of your semiconductors. This I'm telling you for your final board exams. Right now, if in your school semiconductors aren't done, it won't be asked to you from semiconductors. But sometimes this is combined with the concept of this semiconductor. So that's why I'm saying this concept is important, because this can come either from here or from here. So the chances are doubled, no? From 2 lessons if one single topic is present. Write it down, then one formula we have on temperature dependence that we see. Write it down first. See class, this was the formula which I was mentioning you, the resistance variation with temperature. So this formula basically RT is equal to R naught 1 plus alpha T minus T naught. Now RT is what? Resistance at a temperature T. R naught is resistance at room temperature. Room temperature's value will be given to you in the question. Do not assume it because in every question it is different. So that will be mentioned to you, value of room temperature. The other value will be, you'll have to calculate. So 1 plus alpha is coefficient of resistance. It's coefficient of resistance. SI unit is inverse of Kelvin. And this is the temperature difference. The temperature at which you are calculating the resistance is T, and the room temperature for which this was given, that is T naught. So two resistances for two values of temperature. For temperature T, you have RT. For the value of temperature T naught, you have R. Fine. Note down this question, then I'll discuss this question. Then we'll start different topic, EMF and internal resistance and all. Just write this down. See, this question says that an electric toaster uses nichrome for its heating element. Now, when a negligibly small current passes through it, its resistance at room temperature. Now, see, room temperature is specified to you, 27 degrees Celsius. This is 75.3 ohms. Now, when the toaster is connected to a 230 volt supply, current settles to a steady value of 2.68 amperes. So room temperature is given to you as 27 degrees Celsius. So T naught is given to you as 27 degrees Celsius. And resistance also at room temperature. Look here. The resistance also at room temperature R naught, this is given as 75.3 ohms. But you do not have the value of the steady temperature, that is T you do not have, which you have to find out. Alpha is also there in the question. Alpha is also given 1.7 into 10 to the power minus 4. But what about one more resistance? See, this wasn't in the formula. There was one more resistance at this particular temperature. So you do not have the value of resistance, but you do have the information about the potential and current, that is 2.68 amperes. So resistance can be calculated by R is equal to V by I. That becomes 230 divided by 2.68, which is equal to 85.6 ohms. This should be around 85.6. Someone please just cross check. This is around 85.6. So now you have the value of resistance. Now, if you use the formula, RT is equal to R naught 1 plus alpha T minus T naught. See all the values you are having. RT is 85.6 ohms. R naught is 75.3 ohms. One is their constant. Alpha was 1.7 into 10 to the power minus 4 in a degree inverse. T you have to find out. And T naught, this is given as 27 degree Celsius. Fine. So just put in the value, see what is the value of this T is coming. And this way only you have the question. Since some questions you have to calculate the value of alpha. Though in this question it's given. Write it down. Let me know what's the values coming. I remember its answer. So first you people solve it. Let me know what are your answers coming. So I'll tell you what's the answer. Write this down as well. Now then we'll after this start with different topic. Yes, the answer of this, anybody who has calculated? 844.6. Yes, correct. 840.6 degrees Celsius. Around 845. That's correct. So the value of T will come this way. All right. Now let's start with terminal potential difference. Before that, internal resistance. Let us discuss what is meant by internal resistance. So see, whenever we are talking about a cell, in detail, if you go, you people must have had this lesson in your class 12th, I think, electrochemistry. So there you must have done the detailed structure of a cell and everything. So in a cell, just the main basic things, electrodes are present, anode and cathode, these are present, which are dipped into the solution. So these are the electrodes which are present, and this is the electrolytic solution. So electrolytic solution and electrodes both are present. So when the wires are connected to these anodes and cathodes of the cells, when we are having our circuit, so what happens? There is a resistance that is offered by the electrodes also and this electrolytic solution also, which we call as the internal resistance of the cell. Why? See, when we have connected our battery, right? So when we have connected this will also provide resistance. There is an external resistor which you will be connected in your, which you will be connecting in your circuit, right? There will be, it can happen that inductor is also present, capacitor is also present along with these resistors. So many devices are present. But all those are the external devices. All these are the external devices which are present. When we are saying about this cell will also offer resistance. Why? Because when you go into the electrolytic structure of it, you will see electrodes are present and electrolytic solution are present. Ions are present, right? Ions get deposited from anode to cathode, cathode to anode, and all your electrochemistry will be there. So that's why you have internal resistance. And this we depict it by just placing the resistor with the cell. This will be the EMF or potential of the cell, which I'll discuss it. And this will be the internal resistance of the cell. This is the internal resistance of the cell. This is what is meant by the internal resistance of the cell. So this is how you will be depicting it. In wherever you will notice that a resistor is being kept with this cell, it means this is the internal resistance, not an external resistor. Now, any other resistor, why are we seeing internal resistance? Because this is already fit into the cell. You are not placing it, you are not building it, but connecting the external resistors are in our hand. We connect these external resistors intentionally. Fine. Now talking about electromotive force. When we talk about electromotive force, EMF stands for electromotive force. This force, don't go by the term force. This is not a force. This is just a misnomer. No force is present. This is exactly what you studied regarding potential. SI unit is also voltage only. Force is SI unit is Newton. This is not any type of force. This is basically the potential circuit, the potential difference that is applied. See, two terms are present: terminal potential difference and electromotive force. That is the EMF of the cell. When I'm saying electromotive force, EMF, when your circuit is open circuit, when the circuit is an open circuit, then we say whatever is now the potential difference which is connected, that is the EMF. Or you can say whatever potential difference is being exerted here around the internal resistor, that is electromotive force. And whatever external resistor has the values of potential difference, that is terminal potential difference. So main point is that open circuit. So it is the maximum potential difference across the terminals of a cell in an open circuit. Open circuit means off circuit. Current is not flowing. That's why I'm saying you have to focus on the internal resistance. Suppose this is a battery that has been drawn. The higher one, see, I always draw one higher and one lesser. This higher one shows the higher voltage and the lower one shows the lower voltage. So basically EMF is the potential difference between these two, because internal resistor is present here. That's why I'm saying remember it in terms of internal resistor. Internal resistor is already here. So now the potential difference that is being applied, that is this is this potential difference, that is V higher minus V lower. This is what is meant by it. For example, if I give you, this is 10 volts, this is 3 volt. So EMF, if I ask you what is the value of EMF, so you will say 10 minus 3, that is 7 volt. 7 volt is the EMF. So this is the difference that is coming here between this higher one and this lower one. This is called EMF. But when we are talking about the circuit, external resistor is connected, the wire, that potential difference for the circuit, which you have been studying, V, that is known as terminal potential difference. When we are specifically talking about this cell, this becomes EMF. So instead of how to remember which one was what, it's better if you remember it in terms of internal resistor and external resistor. See, one point is there, for open circuit you have EMF, for closed circuit you have potential difference. But it would be better if you remember it in terms of external and internal resistor. See, this is a battery cell. This has its internal resistance. Internal resistance. Key is there. This is the external resistor which I have connected in the circuit. This is the internal resistance of the cell. Here EMF is present. This is external resistor. This is internal resistance. This is EMF of the cell. So now here the potential difference that will be coming, this one will be the terminal potential difference, and here between this higher and lower one within this internal resistor, within the cell, that will be your EMF. These are the three terms which you should be familiar with. Write it down, then I'll tell you the formula part. First write this down. See class, coming to the formula portion. So if we take the circuit, so in our circuit, we'll be having external resistors. Now this external resistor need not necessarily be only a single resistor. I can have groups of resistors which are connected in series and parallel. Ultimately, I'll find their equivalent resistance which will be connected. Series and parallel we'll see this. I hope in today's class only we'll start series and parallel combination. All right. So whatever you get your final answer as R equivalent, that you will be using over here. It does not mean that one external resistor I have kept. Then battery with its internal resistance, there's a switch in your circuit, current is flowing, this is E, this is R. So potential difference across external resistor, see always remember V is equal to IR. This is your which law? Ohm's law. Right? So I into capital R. Potential difference across internal resistors, so I into small r. This is one point which you have to remember. And when we say terminal potential difference across external resistor. Acha, one more thing. See, now current will be what? Current is potential, that is EMF divided by the resistance. If V is equal to IR, so I will be equal to V by R. So potential is EMF here, which is R plus small r. This is the total current in your circuit. So what is now the potential difference equal to across external resistor? Because this is now we are calculating the formula for terminal potential difference. Terminal potential difference is potential difference across external resistor. And what was the potential difference across external resistor? I into capital R. So value of I is E by R plus R multiplied by capital R. One more formula of terminal potential that you have is, see, this is basically the net potential difference. No, potential difference, if you separate the EMF and the potential difference across the internal resistor, rest of which is left will be the terminal potential difference, right? So one more very important formula that is used a lot is E minus, what is the potential difference across internal resistance? I. This formula is also used a lot. All right, E minus IR. We'll see a question also based on this. With this question, let's see. First, write down this point. Class, first write down this question. It's a very easy question, formula based, whatever we have done. Firstly, please have your answers written in your notebook, then I'll discuss it. So while I'm discussing it, you will be giving your answers. So it would be better for you to understand. Because this is the last question that we have to do from this topic. Most of the questions from this topic, no, this is a very basic topic. You will be using this now. So we'll start with series and parallel. By tomorrow, we'll complete also this lesson. Yes, first answer is right answer, 2 amperes. See, this is the external resistance given 10 ohm. Internal resistance is 1 ohm. These second and third part is also correct. Calculate the fourth part also. All the 3 parts are right. Very good. So only she has done. Nobody else has tried. See, for the first part, I is equal to E divided by R plus R. So EMF, this is given as terminal potential difference. Very good. Perfect. So this is 22 divided by 10 plus 1. So 22 by 11, which is 2 amperes, first part. Second part, a potential difference across external resistor. See potential difference across external resistor. This is across external is equal to I into R. So current is 2, external resistor is 10. So that becomes 20 volt. This becomes 20 volt. Then we have potential, third part is potential difference across internal resistor, I into small r. So 2 into 1, which is 2 volts. Last is terminal potential difference. Terminal potential difference is E by R plus R into R. Also, which you can write. So answer will be the same, 2 into 10. That is 20 volt. Fine. One more thing, then you can note down this. So I just wanted to discuss. See, whenever, no, always you are not going to use E minus IR. This is a condition which is known as discharging of cell, means from the positive terminal of the battery, current is flowing. If this reverses, somehow current is flowing from the negative terminal and coming back to positive terminal like this, from the negative terminal, that is charging of cell. In that case, you will use E plus IR. Just keep this in mind. Usually you have discharging only. You will see current is coming from the positive terminal only. But just in case if in your circuit you see that current is coming from the negative terminal, then don't use E minus IR. Then use E plus IR. And if key is open, means no current is there. See, put it in any of the formula. If current becomes 0, potential becomes directly equal to EMF of the cell. All right, write these points also. Write down the above solution also. Then I'll start with the next topic. That completes. This was a very small topic. Then I'll start with series parallel combination. First, we'll talk about the series and parallel combination of the cells. So if you are, we have a separate section we'll discussing tomorrow. We'll be discussing it. If we have identical cells, this is for unidentical cells. When you are calculating the equivalent EMF, what will you do? You will just add it directly. E1 plus E2 plus E3. For equivalent resistance also, you will add it R1 plus R2 plus R3. But this is the condition when your all the terminals are connected in an even order. Like positive is connected to negative, negative to positive, positive to negative, like this. See, negative to positive, negative to positive, negative to positive, like this. But if any of this reverses, if any of these reverses, then we have to have it like this: E1 minus E2 plus, whichever is reversed, that sign will also be reversed. Like, see, this is in the same order, this is also in the same order, this one is reversed. So this becomes minus E2. So one numerical is also there. You have to find the current through each cell. You have to find out the terminal potential difference across the 10 volt. Here you have to find out the terminal potential difference. So see, here for current also we'll be using I is equal to, now E equivalent will be there. The net equivalent. E equivalent we'll be using. And this was R plus, here also you will have now the R equivalent in your circuit. So what current is equal to? EMF is, this is 10 plus 5. See, this E equivalent here, we have 10 plus 5 plus 15, which is equal to 30 volt. And when we are talking about R equivalent, that is 2 plus 2 plus 1. So this is 5 ohms. And external resistor R is 10. So this is the data which you have to put in here. So this gives you 30 divided by 10 plus 5, which is 30 by 15. So current is equal to 2 amperes. Second part says potential difference across 10 volt. Again, see, terminal potential difference, use the formula V is equal to E minus IR. EMF is 30. See, now EMF you will take 10 volt, not 30, because you are calculating it across 10. So 10 minus 2 into, what is the internal resistor for the 10 ohm? It's this 1. So we'll multiply it with. For any of it is asked, just take the individual one. This is answer for the first one. This is answer for the second one. 2 into 1, which is 10 minus 2, that is 8. Note down this. Then we'll start with this series combination first. Let's start with series combination, last topic for today. So in series combination, current will remain same. This I discussed in capacitor also, that charge remains same. So it is series combination. Here current will remain same. So that is series combination. If there is a branching in the wire, then only your current will divide. Otherwise, it is going to be a proper series combination. And voltage will not be the same because of the devices like resistor, which is coming in between, your voltage is not same. So if voltage is not same, so net voltage will be V1 plus V2 plus V3 plus V4 up till Vn. So V is equal to I into R equivalent. That is the, for the total voltage, I'll write total current into total resistance. For the first voltage, I'll write total current into first resistance. For second one, I'll write total current into second resistance. Why am I not writing I1, I2, I3? Because current is same. So I'm using the same variable, which is I. But since resistances are different, that's why I'm using R1, R2 till I into Rn. So current will get cancelled from everywhere. So in series combination, unlike capacitors, you have the net resistance equal to algebraic sum of all the resistors which are present. So R1 plus R2 plus R3 up till Rn, like this you have. So if you have to find out the current through each resistor, current will be the same. Through first resistor, through second, through third, any resistor, if you try to find out, current's value will be the same in them. When we're talking about, that is V divided by R equivalent, which is completely same for which is completely same throughout the circuit. But voltages will be different. I1 R, IR1, I2, IR2, IR3, IR4, like this for every resistor. Power is equal to P is equal to I square R. So when we are talking about the net power, which it is going to be I square into R equivalent. I square into R equivalent. So for the first one, we have I square R1. For the second one, we have I square R2. See, resistance will change, current will be the same for individual. But for the overall, that this is the total power of the circuit. This is the total power of the circuit. Now, one question. So, simple question is there. 5 ohm resistor is connected, 10 ohm resistor is connected. This is R1, this is R2, this is the net current which is flowing within the circuit. Voltage is 10. Now, look here. There is no branching over here. Both the resistors are connected. So, directly means this is the series combination. When we are calculating R equivalent, here R equivalent will be equal to R1 plus R2. That is 10 plus 5, which is equal to 15 ohm. Simple. When I say total voltage of the circuit, total resistance is 15 ohm. Fine, this is the total resistance. Total voltage is already given to you, that is 10 volt. So for this, you don't even need to calculate. Total voltage is given to you, that is 10 volt. This is the total voltage which is being supplied. But when you are asked to calculate total current, so R equivalent is 15 ohm, voltage is equal to 10 volt. This is the total voltage, this is the total current, total resistance. So total current will be potential by resistance. This is also equivalent, this is also equivalent. That is 10 by 15. This is 2 by 3 amperes. This is the total current. So R1 will also be receiving 2 by 3 amperes. R2 will also be receiving 2 by 3 amperes. Fourth part is seeing current in each. See, I told you, I1 is equal to I2, which is equal to the net current of the circuit. So I1, I2 will also be equal to 2 by 3 amperes. Last part says voltage across each. So yes, voltages will be different. When we are saying V1, that will be I into R1. So 2 by 3 into 10. That is 20 by 3 volt. And when we say V2, this is going to be I into R2, which is equal to 2 by 3 into 5. So this is 10 by 3. Look, when I add now to check whether my answer is right or not, if I add these two, that becomes 20 by 3 plus 10 by 3. That is 30 by 3, which is equal to 10 volt. Am I getting 10 volt back? It means this 10 volt is being divided into 20 by 3 and 10 by 3 to both of the resistors R1 and R2. Clear? This is all about series combination. Initially, we are doing the basics of it. Parallel, I'll do it tomorrow itself. First, write down all these points. Then we'll complete the rest of the questions. All those who have completed, you people can leave. Tomorrow we'll do parallel combination and rest of the portions of this lesson. Okay, thank you so much, class. Yes, assessment will be there, Deborah. Assessment will be there.